After we finished the thermistor and the LDR, now it's time to the last component, the transistor. Number 9. Transistors. The image shows a real transistor. It is clear that it has 3 connections. One is labeled E, and the middle is labeled B, and the third is labeled C. How to draw its symbol? You first draw a circle, and then 3 short lines as shown, and then the connections. A transistor is a small semiconductor device. It is made of semiconductor materials like silicon and germanium. A transistor is used as a switch or amplifier. We use the transistor basically as a switch, as it has many advantages over the common mechanical switches. Advantages over other switches: small, cheap, no moving parts, so less probability of being damaged, and that's why it has a long life, can switch on and off rapidly, many times in short time period. Let's go back to the symbol of the transistor and draw 3 connection ends. The first end is named collector. In our case in this syllabus, the collector receives the current from the external circuit. The middle end is named the base, and its function is to control the current coming from the collector. The third end is the emitter. In our case, it's the outlet of the current after passing the transistor. Our main big circuit that will be controlled is connected to the emitter and the collector. This circuit contains a cell, a mechanical switch S1, and the bulb. This circuit in the presence of the transistor has no current because the transistor is normally off. And as you see, whatever you do, making S1 on or off, no current flows because the transistor will not allow the current to flow. It is normally off. But how can we make the transistor on to allow the current flow in the circuit? The theory of the transistor claims that to make the transistor on and allow the current to flow through it between the collector and the emitter, there must be a voltage between the base and the emitter that is not less than 0.6 volts. This is the minimum value for the transistor to work. The simplest way to do this is by connecting an 0.6 volt cell between the base and the emitter. Once this happens, the transistor becomes on and allows the flow of current in the bigger circuit between collector and emitter. The current flows and the bulb lights. In a few words, we can summarize the way transistor works as follows. When the voltage VBE between base and emitter becomes greater than 0.6 volts, transistor switches on and the current flows between the collector and the emitter. Note, if VBE increases, also the current in the main circuit between collector and emitter increases. We can allow more current to flow in the big circuit by increasing the voltage between base and emitter. In this part, we will use the transistor to construct alarm circuits. Mainly, we will study the temperature alarms, like cool alarm and heat alarm. Also, we will study the light alarm, including dark alarm and light alarms. But first, let's quickly revise how transistor works. Even S1 is closed, bulb is off, and there is no current because transistor is normally off. To make it on, we need a voltage greater than 0.6 volt between the base and the emitter. The simplest way to do this is adding a battery. In this case, the transistor switches on, current flows, and bulb lights. A new idea is to get rid of the 0.6 volt cell. Let's start with the cool alarm. Between the base and the emitter, we added a thermistor instead of a cell. This thermistor is in series with a fixed resistor. Let's see how it works. But remember that the condition still applies. There must be a potential difference greater than 0.6 volt between base and emitter. Another thing to remember is the thermistor and the resistor are in series with the main battery. This means that the voltage of the battery is shared between them. The one that has the bigger resistance will acquire a bigger voltage from the battery. The transistor in our circuit is normally off This means that this part of the circuit is neglected, since no current will pass in it. So this becomes our starting circuit: a battery with a fixed resistor and a thermistor in series. The fixed resistor and the thermistor in series will both share the voltage of the battery. Remember that this is a cool alarm. If weather becomes cold and temperature decreases, this means the resistance of the thermistor will increase. You can revise the thermistor part to know how it works. When the resistance of the thermistor increases, its share of the voltage increases. When the voltage across the thermistor exceeds 0.6 volts, in other words, the voltage across base and emitter becomes greater than 0.6 volt, so the transistor switches on and the current flows between the collector and emitter, and the bulb will light. If you have a general overview on the circuit, you find that the bulb will light when weather becomes cold, when voltage across base and emitter becomes greater than 0.6 volt. Transistor switches on and current flows between collector and emitter. Lamp lights. Don't go and just wait for 3 more examples. They will make it clearer. Another example is the heat alarm. The same way of thinking, this part of the circuit can be initially neglected because transistor is normally off. In the heat alarm, these are the positions of both the thermistor and the fixed resistor. So if weather becomes hot and temperature increases, the resistance of the thermistor will decrease. You may revise the thermistor part to remember how it works, so its share of the battery voltage decreases. This automatically increases the voltage across the fixed resistor, which is placed between the base and the emitter of the transistor. When voltage across base and emitter becomes greater than 0.6 volts, the transistor switches on, the current flows between collector and emitter, and the bulb will light. If you have a general overview on the circuit, you will find that the bulb will light when weather becomes hot. When voltage across base and emitter becomes greater than 0.6 volts, transistor switches on, current flows between collector and emitter, and lamp will light, giving an alarm that weather is hot. Another example is the dark alarm. It will work if it goes dark, the same way that transistor is initially off, so we can neglect this part of the circuit. Note that here we have an LDR instead of the thermistor. When it goes dark, the light intensity decreases and the resistance of the LDR will increase. You may revise the LDR part to remember how it works. When the resistance of the LDR increases, so its share of the voltage will also increase. When the voltage across the LDR becomes greater than 0.6 volts, in other words, the voltage across base and emitter becomes greater than 0.6 volts, the transistor switches on, the current flows between the collector and emitter, and the bulb will light. You will find that the bulb will light when the surround becomes dark. One last example is the light alarm. The same way the transistor is normally off, so ignore these parts of the circuit. If light intensity increases, the resistance of the LDR will decrease, so its share of the voltage will decrease. This automatically increases the voltage across the fixed resistor, which is placed between the base and the emitter of the transistor. When voltage across base and emitter becomes greater than 0.6 volts, the transistor switches on and the current flows between collector and emitter. The bulb will light. You will find that the bulb will light when light intensity increases. When voltage across base and emitter becomes greater than 0.6 volts, transistor switches on, current flows between collector and emitter, and lamp lights. For examples to show how the transistor can be used in alarm circuits. There are many other sensors that can be used, like humidity sensor to make the humidity alarm, using the same idea.